Hello everyone, welcome to our presentation on types of collision, exploring how momentum is conserved. I'm Tiffany.
I'm Bachi. I'm Kayla.
And today we're going to be breaking down how objects interact and how they transfer energy and how physics is incorporated into all of this. Okay. Okay, so this is what we're going to go over today. We're going to define what momentum is and the core conservation law, and we're going to be exploring the three types of collision. We're going to start off with elastic collision, where objects bounce off each other. Then we're going to go into inelastic collision, where objects bounce off each other, resulting in energy loss. And then we're going to go into perfectly inelastic collisions, where objects stick together.
Okay, first off, we start with momentum. And momentum represented by P is defined as inertia in motion, which is like the mass of an object times its velocity, P equal to m times b. It represents how difficult it is to stop a moving object and calculate it as mass times velocity, like as we already said. And if the unit for it is kilogram times meter per second. And okay, now let's look at the diagram. So here we have a 4 kilogram ball moving right at a 2 meter per second, and here we have has a moment, and this one have a momentum of plus 8 kilogram times meter per second. And here we have the second ball that moving toward the left, which has a mass of 1 kilogram with a velocity of 8 meter per second. And it also has a momentum of negative 8 kilogram meter per second. And when they collide, which show right here, their opposite momentum cancel out perfectly, which bring both to a completely stop at velocity equal to 0 meter per second. And now that would bring us to the law of conservation of momentum. In a closed system with no external force like friction, the total momentum before a collision always equal to the total momentum after. If the collision is perfectly elastic, kinetic energy is also conserved using the standard formula that we show here. And essentially the initial momentum always equal to the final momentum.
So here's an example of the rowboat recoil. And so if a 60 kilogram student were to stand in a still 40 kilogram boat, because everything is at rest, then the initial momentum is 0 kilograms meters per second. And if the student were to jump forward at 3 meters per second, then if we wanted to find the final velocity, then we would first have to take the initial momentum, set it equal to 0, so that means Pi equals 0 kilograms meters per second, and then we would use the conservation law to set the final state to 0, and then we would substitute and solve, and then we would find that the negative sign shows that the boat recoils and moves backwards at 4.5 meters per second to conserve momentum. Now let's look at three types of collisions, starting with elastic collisions. Here, both momentum and kinetic energy are perfectly conserved, and the physical encounter between two or more objects in which both momentum and total kinetic energy are conserved. So objects bounce off each other perfectly, no mechanical energy is lost, and an example of this is carts bounce off each other when colliding. So they bounce off each other with 0 mechanical energy lost to heat or sound, and you can think of it as magnetic bumper cars or billiard balls hitting each other cleanly.
Hi guys, we're going to be demonstrating elastic collision. Okay, now we have inelastic collision. Momentum is still conserved in this instance, but kinetic energy is lost during the impact. So the lost energy can be converted into things like sound or heat. And things like examples of this could be a car crash where the cars collide and there's damage afterwards, or think any sport like baseball where you're catching the baseball with a glove. And then now we have perfect inelastic collision, and here the colliding objects actually stick together and move together as one combined mass. In this instance, momentum is still conserved, but this type of collision results in the max amount of loss in kinetic energy. An example of this would be Velcro carts collisions where the Velcro carts are locked together or magnets snapping together into one unit.
Hi guys, we're going to be performing perfectly inelastic collision.
Okay, and here we have the energy trend across the different type of collision. In all type of collision, momentum conserved. However, kinetic energy is the different thing between them. Is that in inelastic collision, the kinetic energy is 100% reserved, partially lost in inelastic collision, and finally is experience the maximum drop for perfectly inelastic collision.
So a great real-world application of this is the ballistic pendulum, and it is commonly used in forensics to find a weapon's muzzle velocity. So by firing a bullet into a heavy suspended block, it creates a perfectly inelastic collision. By measuring how high the block swings, investigators can use energy and momentum laws to work backward and find the bullet's exact initial speed. And this was a tool invented in 1742, but it still perfectly demonstrates the concepts that we learned in class.
Okay, and summaries and reflection of what we learned. So we learned that a core concept is momentum is P equal to mv, and measured in kilogram time meter per second represent that inertia is in motion and how difficult it is to stop a moving object. We know about universal conservation law that in any closed system, free from external forces, the total momentum before a collision is always equal to the total momentum after. And the collision spectrum, while momentum is conserved across all type of collision, what different is the kinetic energy. In elastic collision, objects bounce off each other, which zero mechanical energy loss. For inelastic, objects bounce off each other but experience a loss of total kinetic energy during impact. And perfectly inelastic, that objects stick together to move at a single combined mass, result in a maximum possible kinetic energy loss.
Thank
Thank you.